Math 242, Cuesta College. I'm Joe Vasta, and we are going to cover 9.1 sequences. It's not as intense as our last section. Definition. A sequence is a list. That's all it is. It's a list. Now, math people like to ruin it, and they like to say it's a list of numbers. But even in the math world, it could be also a list of functions as well. So basically, a sequence is a list. And what are they going to ask you to do in the homework? They're going to ask you to write out the first 4 terms. Those are the elements of your list, the first 4 terms of the given sequence. And so this right here, this looks weird. This is a subscript. And it says a sub n equals 6n minus 3, and then it tells you where the n starts. N starts, it says n is greater than or equal to 1, so n starting at 1. So I'm going to go ahead and in this formula, I'm going to replace the n's with the number 1. So 6 times 1 minus 3. And so what does this give me? This gives me 6 minus 3. And 6 minus 3 is 3. 3 is the first term of this sequence, which is written kind of in a weird fashion. Now, the next term of the sequence is going to be gotten by putting a 2 into that formula for n. So I have a sub 2 equals 6 times 2 minus 3. And so that looks like it's 12 minus 3, which gives me a 9. Well, they want the first 4 terms, so it looks like I have to find a 3 and a 4. So a 3 is 6 times 3 minus 3, which is 18 minus 3, which gives me 15. And a sub 4 is 6 times 4 minus 3, which is 24 minus 3, which gives you 21. Now, you may have noticed when you were writing these out that you actually saw a pattern. The pattern was, you know, it looks like you're jumping up by 6 each time, and you are. But whether you saw the pattern or not, your answer happens to be 3, 9, 15, 21. Now, they just asked for the first 4 terms. They could have asked for the first 100 terms or the first 1,000,000 terms. A sequence like this has infinitely many terms. So good thing they just asked for the first 4 terms. There's our answer. Okay. So let's go ahead and do some more problems, because this is what you do in your homework. Not as intense as some of the other things we've done in this class. So sequences can be written like a sub n, but sometimes they'll switch it around on you, and this one here says b sub k. b sub k equals, here's the formula, -1 to the k times k plus 1. So k actually starts, look, it says k is greater than or equal to 0. K starts at 0. So in the last one, the letter started at 1. They're going to tell you where it starts. So if k is 0, you have b sub 0. That is the first term of your sequence. So this is going to be everywhere where there's a k, you replace it with a 0. You might think that it's kind of dumb to start your counting at 0, but computer scientists love it. So anything to the 0 power, -1 to the 0 power is 1, and then we have 0 plus 1 is 1. So the first term of this sequence is a 1. Let's put k equals 1 in. And the last problem, I didn't write that off to the side because we were starting at 1, but this is a little weird. So k equals 1 into the formula. b sub 1 equals -1 to the 1 power, and then we have 1 plus 1. So -1 to the 1 is actually a -1 now, and a 1 plus 1 is 2. So our second term is -2. K equals 2 is going to give us our third term. So everywhere in this formula where there's a K, I'm going to replace it with a 2. B 2 equals negative 1 to the 2, or we say squared, and then we have 2 plus 1. So negative 1 squared, that's actually going to give me a positive 1 again. And then we have 2 plus 1, which is 3. Now you might be looking at this and saying, I know what the pattern is. And maybe we do. But I want you to look at this right here. Pay attention to this negative 1. It keeps alternating from positive to negative to positive, and then the next one's going to be negative 1 to the 3, so that will be negative. When I teach calculus 2, I like to call that a light switch, because it's turning on and off. Let's put k equals 3 into this formula for k. We have b sub 3 equals negative 1 to the 3, 3 plus 1. So negative 1 cubed is negative 1 times negative 1 times negative 1, which is negative 1. And then we have 3 plus 1 is 4. So this gives me a negative 4. So maybe you saw the pattern. 1, negative 2, 3, negative 4, 5, negative 6. Well, in any case, we only need the first 4 terms. So 1, negative 2, 3, negative 4, and that's my answer. Find the first 4 terms of the given sequence. Let's go ahead and do a few more problems. So here's another thing to realize, that some books will define a sequence as a function. So this almost reminds you of maybe b of k, with parentheses, where the input happens to be natural numbers or whole numbers and the output is a real number. Okay, so some books go crazy and say, hey, look back at this one right here. So this one right here where it says a sub n is 6n minus 3, it may have reminded you of the function of f of x equals 6x minus 3. And some books will be really big on, graphing sequences, which would be a series of dots. The first dot being 1, 3 and 2, 9. But we're not going to do that in here. Go ahead and do problem number 3, and this is probably going to traumatize some of you. Look at this. The formula is now in these braces, and then look, here's your starting point, n equals 1, and then this is where you're going up to. Well, you're never going to make it to infinity, but this is just notation for a sequence. The disadvantage with this notation is that we don't have a name for this. We don't say, oh, well, this is the sequence c sub n or whatever. But let's go ahead and write out the first 4 terms. N equals 1 on this sequence. We're going to put 1 in for n in this formula. So this is 1 minus 1 over 1 squared. So this is 0 over 1. The first term is 0. So this is all you're doing in your homework for the first part. N equals 2. So I have 2 minus 1 over 2 squared. This is 1 over 4, which is 1 over 4, 1/4. N equals 3. We have 3 minus 1 over 3 squared. This is 2 over 9. N equals 4. So we're starting at 1 this time. In the last problem we started at 0. And they tell you where you're going to start. You have 4 minus 1 over 4 squared. This is 3 over 16. So the first 4 terms of this sequence would be 0, 1/4, 2/9, and 3/16. So this also goes to show you that sequences can have numbers that are fractions. They can even have numbers that are square roots and irrational numbers. So there it is. Let's go do problem number 4. Which looks like this. Okay, so look at this. This is K is the letter that we're changing on. K goes from 0 to infinity. I'm going to start off with K equals 0. Now here's a crazy part about this sequence. It has another letter in it, and that would be X. So as we are changing the values of K, we keep X the way it is. So when K is 0, I have 0 plus 7 And then we have x to the 2 times 0 power. So what is this really? This is 7x to the 0, which is 7. Okay, let's try k equals 1. I put 1 in for k in this formula. So where am I putting these values? I'm putting them right here and right there, but not on the x. So I end up getting 1 plus 7, and then we have times x to the 2 times 1. So this is 8x squared. K equals 2. I'm putting that everywhere I see a k, I put a 2. So I have 2 plus 7. This is x to the 2 times 2 power. So this is 9x to the 4th. And then the last one that I want to put in happens to be k equals 3, because they asked for 4 terms. I have 3 plus 7. Then we have x raised to the 2 times 3. So 2 times 3. This is 10x to the 6th. You may have been able to see the pattern. 7, 8x squared, 9x to the 4th, 10x to the 6th. Maybe the next one would be 11x to the 8th. But we don't really need to do that. You can plug that in the formula if you really want the 5th term. So I'm going to write out the first 4 terms. And they look like this. So we have that. Now, I know I'm always going back to the first example here. This first example, if I really want the 100th term, I could put a 100 in for n and get 600 minus 3, which is 597. So I can find the 100th term or even the 1,000,000th term. And so when all of our sequences we've seen so far with the formulas, you can plug in higher numbers and jump right to the 100th term or the 1,000th term. When you have a formula that does that, that's called an explicit formula. And so problems 1 through 4 are explicit formulas, because you can just plug a 100 in and find the 100th term, a 100 or whatever. 5 through 8 are called recursive formulas. And here is a recursive formula. It's very hard to find a 100 on this one. As you can see, if you put a 100 in or even a 99 in for n, then this equals, so if n is 99, then you have a 100 equals a 99 minus 4. So this one's different, and this pops up a lot in the real world. So how am I going to do something that is an explicit formula? The values for n start at 1 for this formula. I'm going to focus in on this formula. Let's circle this formula. And I'm going to start my n at, see, it tells me where to start it at 1. And so I'm going to get a sub 1 plus 1. I'll write that down. That's in the subscript. This equals a sub 1 minus 4. So this really says a sub 2 equals a sub 1. Now, do we know what a sub 1 is? Yes, they gave it to us. A sub 1 is negative 1. So we have negative 1 minus 4. So a sub 2 equals negative 5. And so let's just write that right after here. So a sub 2 is negative 5. Now the funny part about this is they ask for the first 4 terms. They give you the first term. So you already have part of the answer. You have 25% of the answer, negative 1, and now we have negative 5. So now what I'm going to do is I'm going to let n equal 2 to figure out my next term. And so when I put 2 into this formula, it gives me a sub 2 plus 1, so a sub 3 equals a 2 minus 4. Okay, so just like when we knew what A1 was, and we plugged it right here, now they're saying here is A2, and we are plugging it into that formula. So this is, let's just put it over here, this is going to be -5, that is A2, minus 4. And -5 minus 4 is -9. So A3 is -9. So you can think of the recursive formula as stepping stones. And you needed this stepping stone, you're going across a river to get to this stepping stone. And this stepping stone, A3, is going to help you step to the rock that says A4. How am I going to get A4? By looking at this formula and putting n equals 3 in there. So I end up getting 3 plus 1, so this is A4 equals A3 minus 4. So I got that from the yellow formula. And so now A3 is -9. And then we have minus 4. So let me just circle this to be consistent. And -9 minus 4 is -13. So A4 is -13. I don't need to put a color on that one because I'm pretty much done with the problem. I found the first 4 terms of this sequence. They are -1, which they actually gave us. Now, if they didn't give us this, we would have a hard time generating the rest of the sequence. Then we have -5, -9, -13. And you might actually see the pattern. You're subtracting 4 each time to get to the next one, and that is the pattern. So that's our first recursive sequence. If you're going to be a computer scientist, this is going to be very important that you know about recursion. Let's go ahead and do another recursive formula. 5 through 8 will be recursive formulas, and they will ask for the first 4 terms of the given sequence. So right away we know that our first stepping stone is this guy right there. B0 equals 3. And where, okay, so our index is now j, so our variable is j. And j starts where? Greater than or equal to 0? It starts at 0. J equals 0. So I'm going to copy the formula down, this being the formula. This is what I copy down each time. And I'm putting j equals 0 in there, so this is going to give me b0 plus 1. So b1 equals -2 b0 plus 1. And we know what B0 is. B0 is what they gave us. So this gives me -2 times 3 plus 1. Okay, so -2 times 3 plus 1, that's -6 plus 1, which gives me a -5. And so I'll be consistent with my colors here. So it looks like I got B1 equaling a -5. I'll go ahead and circle that one in blue. Okay, so here's my first term. My next stepping stone is -5. And then let's see what the next one is going to be. I'm going to let j equal the next integer up, which is j equals 1. And I'm going to plug it into that yellow formula. B2, 1 plus 1. This equals -2 b1 plus 1. And do I know what b1 is? Yes, it's this stepping stone here. I'm going to put that right there. So this is -2 times -5 plus 1. Left some space so I can circle that in blue. So what do I have? I have -2 times -5, which is 10. 10 plus 1 is 11. So it looks like I just found B2. B2 is 11. And we are going to have to pick another color for that. I'll pick red for this one. We have one more term to find because we have 3 of them right here. You might be able to see the pattern, maybe you don't see the pattern, but let's just go ahead and plug j equals 2 into the yellow formula. So this is b of 2 plus 1, which is 3. We have negative 2 times b2 plus 1. So do we know what b2 is? It's that guy right there. So we're going to replace that thing with an 11. So this is negative 2 times 11 plus 1. So this gives me a negative 22 plus 1, which is a negative 21. b sub 3 is negative 21. You know what, I'll go ahead and circle that one in a color just so it doesn't feel left out. We have the first 4 terms, our first 4 stepping stones. So we have 3, comma, negative 5, comma, 11, comma, negative 21. And we can keep going if you want. Oh, well, no, we can't. I'm not going to, but you could keep writing out terms in the privacy of your own house. Let's go ahead and do another recursive formula. And so this is problem number 7. Problem number 7, here's our formula, which I'll circle in yellow. Whoa, having a hard time circling things. And our first stepping stone is C0 equals 1. Our n starts at 1 because it says n is greater than or equal to 1, so that's the first thing I'm going to write down, n equals 1. If we notice our formula, it not only has n's in it, but it also has an x. So I'm going to keep the x how it is, and we're going to write out this formula where n is 1. So C1 equals x. So what do we have here? To the 1 minus 2, 1 minus 2 power, plus c sub n is 1, so c sub 0. Okay, so we have a c sub 0 there, and this gives me x to the negative 1 plus 1, which is really, across the line change the sign, because this is really over 1, we have 1 over x plus 1. That right there is my next stepping stone. This, so I'm being a little lazy now, this is actually equal to C1. Let me just go ahead and do that right there. Okay, so now I'm going to let n equal 2, and I'm going to write out the yellow formula. So C2 equals x to the 2 minus 2, so that's, I'll write that up, 2 minus 2 plus c sub 2 minus 1, so c sub 1. That right there is purple. And x to the 2 minus 2, that's x to the 0. And then we have plus 1 over x plus 1. Well, what do we know about x to the 0? X to the 0 is 1. Combine like terms, and you end up getting, it doesn't matter which order you write this in, 1 over x plus 2, which happens to be our C2. And so we'll circle this one in red. Okay, so we're not just getting a sequence of numbers, we are getting a sequence of functions, and I believe that happened. I don't know if I pointed that out. That was problem, I don't even know what problem it was. It was problem number 4, where we got 7, 8x squared, 9x to the 4th, 10x to the 6th. It wasn't just numbers anymore, it was a sequence of algebraic expressions. So n equals 3. We're putting 3 into this formula. We have c sub 3 equals x to the 3 minus 2. So I'll just say x to the 1 plus c. And this is going to be C2. C2 being the red. So what do I have? I have x plus 1 over x plus 2. And so this equals C3, and some of you are saying, maybe we should get a common denominator. Well, maybe you should get a common denominator. I'm going to keep it like this. And my 4 stepping stones are right there. 1, 2, 3, 4. So let's write out the answer. Here's my answer. 1, and then we have 1 over x plus 1. And then the next one is 1 over x plus 2. And then the last one, or the fourth one, is x plus 1 over x plus a2. Those are the first 4 terms of the sequence. A sequence is a list. Lots of times it's a list of numbers, and this time it's a list of functions. Let's go ahead and do our 8th problem that has to do with writing out the first 4 terms of a sequence. Here is problem number 8, and it looks like this. So you notice how they always give you like the first 2? Well, now this says f1 equals 1, f2 equals 1, and then this one starts at 3. So they've already given you half of the answer. Write out the first 4 of them. Watch this. N equals 3. So I'm going to write out this formula with an n equals 3 in it. So this is f sub 3 equals f sub 2 plus f sub 1. So really f3 equals, here they are, 1 plus 1. And I'm not going to do a lot of the colors on this one. This one is 2. Okay, n equals 4. This is going to give me f4 equals f3 plus f2. So f3 was 2, and f2 is 1. So this gives me 3. So I've just found 2 of the stepping stones. They gave me the first 2 stepping stones. My sequence looks like this. 1, 1, 2, 3. So there's the answer. But if you wanted to keep going, you might see a pattern. And what you're doing to get the next number is going to be 5, is it says it right here. You're adding the previous 2 terms. 2 plus 3 is 5, and then look at this. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 34. 55. 89. Now, why am I getting so happy with this one? Because this is a famous sequence, probably the most famous sequence there is, the Fibonacci sequence. There was a mathematician named Fibonacci who posed this problem with rabbits on an island. But let's go ahead and talk about a few things about the Fibonacci numbers. So you probably want to Google Fibonacci sequence or Fibonacci numbers. And what you'll find is that there are certain plants that if you count the number of petals, you end up getting a Fibonacci number. Leaf arrangements on certain plants can be arranged in terms of Fibonacci numbers. If you count the number of spirals on a mature pine cone or a pineapple or even a sunflower, they have spirals, you'll most likely count a Fibonacci number. Okay, let's look at piano scales. If you go from C to C, like they first make you do a scale, that scale has 8 notes that you would play. If you included the black keys on the piano, it would be 13. And how many black keys are in an octave? 5. Let's talk about another example, the bee colony. And so with the bee colony, you've got the queen, and then you've got the workers, those are the females who produce no eggs, and then you have the drones, which are the males. And the females are created from a male and a female, but the drones, the males, only have a mom because they are created from an unfertilized egg. So I went ahead and I drew the genealogy of the male bee. So look at this. Here's the male bee. He just has a mom. He just has the female for the parent. And then she has 2 parents. And then everywhere there's a male, it just has a female for a parent. And it goes up like this. Well, where are the Fibonacci numbers in each generation? 1 in the first generation. And then 1, 2. How am I getting that? I'm counting these. 1, 2, and then in this generation has 3. 1, 2, 3, 4, 5. And it just keeps going. 1, 2, 3, 4, 5, 6, 7, 8. And if we did the next one, we'd have 13 and 21. And so there's the Fibonacci numbers in nature. This is more of a concrete example. I didn't bring a pine cone here to show you. Now the Fibonacci numbers had a recursive formula. Is there an explicit formula for the Fibonacci numbers where you can put an F100 in and you can crank out what the 100th Fibonacci number is? Yes, I'm going to show you the most simple recursive formula. And here it is. This may shock you, but if you put a 1 into this formula, lo and behold, the square root of 5's will all cancel out and you'll end up getting 1. You can do it on a computer or on a graphing calculator or wherever you want to do this. If you put a 2 into this formula, guess what you get? You get 1. You put 3 into the formula, you get 2. You put 4 into the formula, no one wants to do that by hand, but by the time it's done, you'll end up getting 3. If you put 8 into the formula, you get 21. So there is, you won't have to know how to do that on the exam. So those are the Fibonacci numbers. And so that will complete the part of the homework where it asks you to write the first 4 terms of a sequence. Now we're going to go ahead and introduce you to some other kinds of things. So here's another kind of problem where you're given a sequence, and there's one here too, and you're supposed to guess what goes in the box. So you can pause the video and see if you can guess what goes into, both of these boxes if you want. Okay, so a common thing that people do is they go ahead and they say, well, what are the gaps? Look, you add 3 here, and you add 3 there, and you add 3 there. And so it seems like the pattern is you just add 3. And so what you end up getting for that one is 14. When you add the same number to get to the next term of the sequence, this sequence has a name. It's called an arithmetic sequence. Now, it looks like when I wrote that down that I wrote arithmetic, but it's an arithmetic sequence. And the number that you add to get to the next term is called the common difference. And the common difference has a letter that they always use. It's called D. And for this example, the common difference is 3. So that is an arithmetic sequence. Did you figure out what goes in here? I mean, if you add 4 and then add 4, you're not going to get it. And some of you already figured it out. You don't add a number, you multiply. So we multiply by 3, and then you multiply by 3 again. And then there wasn't much to go on this one, so this one may have been harder for some of you. You multiply by 3 again. 18 times 3, it's 54. So this is not an arithmetic sequence, this one right here, because arithmetics, you are adding the same number. Or, you know what, arithmetic, you could also subtract the same number because you're really adding a negative. This one is multiplying, so it has a name as well, and this sequence is called a geometric sequence. So the geometric sequence is gotten by multiplying the same number to get the next term, okay? And so the number you multiply by is not called the common difference, but it's called the common ratio. I used to hate that word just because, first of all, I never liked ratios when I first saw them, and then it just doesn't, radio or, it just doesn't, it always freaked me out when I first learned it. So it has letter R, and so in this example, R is 3. So what they're going to do in the homework is they're going to ask you, are you looking at an arithmetic sequence, a geometric sequence, or none of them? So let's go ahead and do a few more problems. We'll guess what's in the box. We'll analyze these sequences. So here it is. This is what you'll see in your homework. We could have written this out for the first two problems, but if I did, you would have been confused. You would have been like, well, what are those things? So let's see. Find the next term. We can do that. Determine if the sequence is arithmetic, geometric, or neither. If it is arithmetic, find the common difference D. If it is geometric, find the common ratio R. So you might want to pause the video and see if you can see the pattern here for this sequence, what goes in the box. Okay, so if you start looking at the gaps, you add 2 there, and then you add 3 there. Okay, so that doesn't look like it's going to be arithmetic. Arithmetic has to be the same number. If you multiply by 3, 1 times 3 is 3, 3 times 3 is 9. Yeah, okay, so it is not geometric either. Let's continue to look at the gaps. So the gap between the next 2 is 2. And then, right here, the gap is 8. Okay, so that's weird. And then over here, the gap is 2. Okay, so that's a little confusing because there's a 2, the 3. Okay, so some of you may have realized that, but this is how you do it. You just troubleshoot it. This is what real mathematicians do. They don't sit in their offices saying, okay, I'm going to do 1 through 119 odd in the math book. They actually look for patterns. So some of you may have noticed that, yes, you add 2 first time, and then when you go from 3 to 6, another way of doing this is saying that, well, maybe, I mean, sure, yeah, you can add 3, but another way of looking at this is you multiply by 2. Okay, and then you add 2, and then look at this one. We multiply by 2. That seems to be fitting the mold. You add 2, multiply it by 2, add 2, multiply by 2, add 2, and then we multiply 18 by 2, we end up getting 36. So is it arithmetic, geometric? Some of you would say it's a hybrid, but we're not going to use that word hybrid. We're going to use the word neither. Because it's not truly arithmetic and it's not truly geometric. So that's what it is. Let's go ahead and do another problem. It's problem number 4. Is it arithmetic? Is it geometric? Neither. And then if it's one of those, you have to find the common ratio or common difference. So what are we doing? Like if you subtract, let's just subtract 12, and then you subtract 12. So we can see that the gaps aren't consistent, especially with those fractions. So we know this thing is not arithmetic. Let's see if it's geometric. Well, it's hard to say what you would multiply by. I know some of you would say, well, you're dividing by 3. And then look, you divide by 3. But when you're dividing by 3, you're really multiplying by 1/3. So you could still say divide by 3. And look, you divide by 3. You end up getting 2. And then you divide by 3 again, you end up getting 2/3. So let me just say multiply by 1/3 each time. That seems to be the pattern. And so multiplying by 1/3 again puts what's in the box, which would give me a 2 over 27, 9 times 3. So that's the next term. We can see that this thing is geometric. This is a geometric sequence. And then they said, if it is geometric, find the common ratio R. Well, we kind of already see it on the paper there. R is 1/3. And so a geometric sequence can also be thought as one where you divide by the same number. And that's really multiplying by 1/3. Let's go ahead and do a few more problems here. Problem number 5. So it says a sub n equals 30 minus 10n. N is greater than or equal to 1. So n starts at 1. Let's write out the first few terms. If n is 1, you have 30 minus 10. So then you have like what, a 20. And if n is 2, you have 30 minus 20, which is 10. And n is 3, you have 30 minus 30, which is 0. So you can verify this on your own if it's going a little fast. You could probably already guess what's happening here. Oh no, what did I do? If n is, oh gosh, n is 1, n is 2, n is 3, n is 4, you end up getting 30 minus 40, which is negative 10. No one's going to even know that I forgot those negatives when they're looking at the PDF. Okay, those are negatives there. Okay, so what am I doing to get to the next term? So some of you might say, hey, you are subtracting. You're subtracting a 10. And that is correct. But, you know, for those of you who are saying you're subtracting a 10, you're really adding a negative 10. I used to hate when my math teacher said that. When you're subtracting, you're really adding. It's like, you know, Darth Vader betrayed Anakin. You know, I mean, it's almost like they're telling you something that's deceptive. But it's true, actually. You know, I'm with Obi-Wan Kenobi on this one. When you are subtracting a 10, you're really adding a negative 10. And so look at this. I'm subtracting the same thing. I didn't have a box, and you know, so we're not going to find the next term because we could say the next one is negative 40. But I'm going to say that this guy is arithmetic. Arithmetic. And that our common difference is going to be, or is, negative 10. So there's the answer. There's one whole piece of paper for this problem here. You're going to be actually more disappointed in me when you see the next piece of paper and you're like, whoa, a whole piece of paper for this. 1, negative 1, 1, negative 1, 1, negative 1. Whew. So what is this? Okay, so you think about it and then pause the video, come back and see if you got it right. What am I doing? If I'm subtracting 2 and then subtracting 2 again, that's not going to cut it. But you could say, look what I'm doing. I'm multiplying by a negative 1. Okay? Multiplying, it's kind of the weird notation here, by negative 1. Multiplying by negative 1. So it looks like what I have here is a geometric sequence where your R is negative 1. Okay, so sometimes R can be negative and sometimes D can be negative, as we saw in problem 5. Let's go ahead and do this problem. Do you see the pattern? And most likely you do. 1, 1, negative 1, negative 1. 1, 1, negative 1, negative 1. 1, 1, negative 1, negative 1. So is this arithmetic? If it was arithmetic, to get from here to here, you would add 0, and then you would add a negative 2, and then, yeah, it's not going to be arithmetic. Is it geometric? To go from here to here, you would go 1 times 1 is 1, and then 1 times negative 1. So we don't have a common ratio. So this is going to be neither. And you're saying, Joe, come on. A whole piece of paper for this. And I would say, no, I was actually planning on drawing a picture here. And there are actually going to be people who skip the videos and they're just looking at the PDFs, and they're going to get to this and they're going to think, what just happened? Is he using this picture to analyze the sequence? Absolutely. Let me go ahead and make this a little bit. There's the bark on the tree. Oh, I think I messed it up there. Oh well. Okay, so now you can't say I wasted paper. Look, I put a nice tree there. Let's go ahead and do the next problem. Problem number 8. Okay, so this says A sub n equals n. Okay, so the first thing we realize is, you know, we're not going to say that with excitement. This is actually called n factorial. This is going to be seen in calculus as well. And so like a sub 0 is 0 factorial, A sub 1 is 1 factorial. A sub 2 is 2 factorial. A sub 3 is 3 factorial. Okay, so what are these factorials? I have not defined them yet. Let's start off with 3 factorial. 3 factorial is really, you start off with 3 and you count down until you get to 1. So 3 times 2 times 1. So 3 factorial is 6. 2 factorial is 2 times 1. 2 times 1 is just 2. 1 factorial is just 1. And 0 factorial, well, what is that? Well, it's defined to be 1. So your sequence could have been written like this: 1, 1, 2, 6. By the way, what is 4 factorial? Well, that would be 4 times 3 times 2 times 1. So that's 24. So really what you're doing is you're multiplying by 1, and then multiplying by 2, and then multiplying by 3, and then multiplying by 4, and then you would multiply by 5 to get the next one. So you're not multiplying by the same number, so this one's going to be neither. It's not arithmetic, it's not geometric. Now let's say a few things about factorial, because this upsets people, that 0 factorial is 1. They want it to be 0. Let's go ahead and tell you what factorials mean. Okay, you got a movie theater. If you're lining up 3 people. This is Alice, this is Bob, this is Charlie. Great cryptography names. How many ways can you line 3 people up to the movie theater? Well, 3 factorial. There's 6 ways. How many? I'll list out the 6 ways, okay? So I'll make tally marks every time I say one. So Alice, Bob, Charlie, Alice, Charlie, Bob, Bob, Alice, Charlie, Bob, Charlie, Alice, Charlie, Alice, Bob, and Charlie, Bob, Alice. So there's 6 ways to line these people up. Okay, so what's going to happen? We're going to get rid of Charlie. Charlie's usually the bad guy in cryptography anyway. He's the guy listening in the middle. I have 2 people and I want to line them up at the movie theaters. How many ways can I do that? 2 ways. 2 factorial. I'll tell you the ways. I'll make tally marks as I say the ways. Alice, Bob. Or you can go Bob, Alice. So there's the 2 ways. Looks like 11, but those are my tally marks. Okay, let's get rid of Bob. This is really dumb. So it's your job to line people up at the movie theater. Only Alice arrives. How many ways can you line Alice up at the movie theater? 1 way. And I'll tell you the way and make tally marks as I tell you the way. Alice. Okay. Nobody comes. It's still your job to line people up. This does not look like good social distancing, by the way, so please do not report me to the authorities. Nobody comes. How many ways can you line nobody up if that's your job? Well, 1 way. There's 1 way to do nothing. If you don't like that, then go back to this where I tell you that that is a definition. If you think that the tree is going to confuse people who are just looking at the PDF, think again. This is going to be more confusing. Okay, so what we have done is we have lots of things to say. We learned about arithmetic and geometric sequences. Let's take a look at this. Is going to get a little abstract for some of you. So arithmetic sequence. Okay, so arithmetic sequence. This is very abstract. The first term we're going to call A. And the common difference we're going to call D. Let's go ahead and list out the first few terms. Now some of you are saying, well, Joe, you're very abstract. Well, I am. So A1 is A. And A2 is, well, the common difference is D. It's going to be A plus D. If you want, fast forward through this video until you actually get an example, where it says example 1. A3 is actually going to be A2, which is this guy right here, and then you're going to add D again. So A3 is A plus 2d. Well, what do you think a4 is going to be? It's going to be a3, which is a plus 2d, plus another d. So a4 is going to be a plus 3d. And what's a5 going to be? So we can see the pattern. It's going to be a plus 4d. And a20, I know I jumped a little, or a lot. It's going to be a plus, so look at the pattern here. There's a 5 here and a 4 there, and there's a 4 there and a 3 there. So this is going to be a plus 19d. So what do you think an is going to look like? It's going to be a plus, 1 less than n is n minus 1 times d. So the official formula, this is called the nth term. The nth term for the arithmetic sequence looks like this. A sub n equals, now I'm going to go back to calling this a1. a1 plus n minus 1d. n minus 1d. And I'll say this formula is going to start off at 1. And there it is. So that's a formula we're going to be using when we do maybe some of the homework problems. Now I'm going to do the same sort of abstract, creepy math, but now I'm going to do geometric sequences. So this is going to look similar, but it's still going to look abstract. So we have a geometric sequence. And its first term is a, and its common ratio, I'd better not abbreviate that. Common ratio is r. Okay, let's go ahead and write out the first few terms. a1 is the first term, a. a2, well, how do I get to the next term with a geometric sequence? I'm going to take the first term and multiply it by r, so this is going to be ar. a3 is going to be the last term, ar, times what? Times the common ratio. So r, so it's going to be ar squared. And a4 is going to be ar squared times r, which is ar cubed. a5 is going to be ar to the 4th. a20, I know I went ahead and jumped a few. This is going to be ar 1 less than the 19th. So a sub n, if you can guess that, then you've got the formula there. This is going to be ar to the n minus 1. So we have the nth term for the geometric sequence. Looks like this. A sub n equals ar to the n minus 1, but I'm going to call this first term a1. So I'm going to say a1 r to the n minus 1, and then I'm going to say n starts at 1. So those are some important formulas. If this were a face-to-face class, I would say I would give those formulas to you. But this is remote learning, so I guess you can look those formulas up when you're taking the test. Let's take a look at the last grouping of problems. This is quite a long section here. Yes, this is the last grouping of problems. And this problem says, find an explicit formula for the nth term. There's actually a few ways of doing this problem. I'm going to go ahead and stick with the formula first, and then after I do the formula way, I'm going to show you another way and see which way you like better. Okay, so first of all, we have to classify this sequence, and you can see that it has gaps of 4, so you know that this is going to be arithmetic, and you know that the value of D on this one is 4. So the arithmetic formula, so the one that we derived, looks like this. It looks like A sub n equals A1 plus n minus 1 times D. This is for n greater than or equal to 1. So what we're going to do is we're going to say, well, we're trying to find the nth term, so we don't know when n is. We're just going to keep it like that. We know D is 4, and we also know A1. What is A1? It's this guy right here. A1 is the first term. So I'm going to just plug that into the formula. A sub n equals A1, which is 1, plus n minus 1 times D, which is 4. So let's simplify the right-hand side of this equation. 1 plus 4n minus 4, so A sub n equals 4n minus 3. And we better put this right here, that our sequence starts at 1. There's our answer. That is the textbook way of doing the problem. Now I'm going to show you another way, and I'll show this way in blue. It will be over here. Lots of times when I see that I have an arithmetic sequence, I can see that the gaps are 4, and I just go like this. I say A sub n equals, and I'm just going to go ahead and put a 4n there. So, is that the formula where start n equals 1? No, because if I just had a 4n there, I end up getting 4, 8, 12, 16. And what am I after? I'm after 1, 5, 9, 13. So I've overshot my sequence that I'm trying to get by 3. So to undo that, I should probably subtract 3. And then when I put a 1 in there, I get 4 minus 3, which is 1. And then put a 2 in there and get 8 minus 3, which is 5. And so n starts at 1. And that's how I will do some of the arithmetic sequences. And it's just kind of finding out what the gap is, starting off with that, and then tweaking that number until you get right on there. Okay. Now, a lot of teachers may not show you this way. This really is the more common way of doing the problem. Let's go ahead and do another problem. Okay, so what are the instructions? The instructions are find an explicit formula for the nth term. Well, look at this. I subtract 3, I subtract 3, I subtract 3. This guy is arithmetic, where my D is not 3, but it is negative 3. Okay, so the textbook way says, look at this. This is A1, and we have a formula that says A sub n equals A1 plus n minus 1 times D. This is for n greater than or equal to 1. So I have an equals A1, which is 7, plus n minus 1 times D. D is negative 3. So A sub n equals 7 minus 3n plus 3, distributing that negative 3. A sub n equals negative 3n plus 10. Our n starts at 1. Now, when you get done, if you don't trust yourself, you could just put 1 into the formula and see that you get 10 minus 3, which is 7. And then put 2 into the formula, 10 minus 6 is 4. Let's go ahead and do it my method. My method says this. I saw right away that the gaps are negative 3. So I'm going to go ahead and write out my formula where it says A sub n equals negative 3n. Okay, so I'm after this. 7, 4, 1, negative 2. And what am I getting? When I put 1 into the formula, I'm getting negative 3. And then I put 2 into the formula, I'm getting negative 6. I put 3 into the formula, and I'm getting negative 9. And 4 into the formula, I'm getting negative 12. So it seems like I'm off by 10. It seems like I really wanted my first term to be 7, but I'm like 10 below that. So to compensate and bring me up to 7, I'm going to add 10. So I put 1 in there, yeah, 7. Put 2 in there, Negative 6 plus 10. Yeah, so it's this thing starting at 1, and there's the way that I will sometimes do these problems. Okay? So some of you are going to like this way because it's clean. There's a formula that works. And others will like this because it's less writing, and you're just you're troubleshooting, you're tweaking it. Okay, maybe the engineers might like this. I don't know. Let's go ahead and do another problem. Problem number 3. So using these formulas that we derived, and now let's take a look at this problem here. The sequence looks like this: 20, 40, 80, 160. So your first question is, what kind of sequence is this? And so what I'm getting for this sequence, it's geometric, where my R is multiplying by 2 each time. So that is what we have. And what am I going to do? Well, I have the formula that says this. Well, the first thing I want to realize is this is A1. The instructions are find an explicit formula for the nth term. So I've got the formula, since this is geometric and not arithmetic, I'm actually going to grab this formula right here that we derived, A1, R to the n minus 1 power for n greater than or equal to 1. So I know what A1 is. A1 is 20. So I'm going to put 20 right there. And I know R is 2. So we have 2 to the n minus 1 power. This is n is greater than or equal to 1. So is this a legitimate formula? Yes, it is. Will it be the answer you see when you flip over the page and look at the answer? It might not be. And I'm going to tell you why. So I'm going to go ahead and show you that this is what your book might do. Your book would say, well, 20 actually is 10 times 2. And then we also have times 2 to the n minus 1. And then they'll put these guys together and say this is really 10 times 2 to the n power. And that's how they'll sometimes, that's how some books will do it. So this formula yields the same results as that formula. I mean, you put 1 in here, you're going to end up getting 20. You put 2 in there, you're going to end up getting 20 times 2, which is 40. You put 1 in here, you get 10 times 2, which is 20. So both formulas are good. You might have asked, why didn't they just write this as 5 times 2 and then write it as 5 times 2 to the n plus 1? You can do that if you want. But in any case, the formula is not like unique. You can write it like this or even another way, and that's how you do these problems. Now if you wanted to know how to do it the other way, I can see this might be a little tougher for people, but I know that my a sub n is going to be, so I see the 2 there, and instead of going 2n, I'm going to go 2 to the n power. And so what I'm trying to shoot for is 20, 40, 80, 160. And right as it stands, I end up getting, for this, when I put 1 in there, I end up getting 2. And I put 2 in there, I end up getting 4. And then I put 3 in there, and I end up getting 2 cubed, which is 8. And 4 gives me 16. So like, I really did a bad job. But I could do what to each of these numbers to get up to the 20, 40, 80, 160. I can multiply each of those numbers up there by 10. And so look, the other method does work. But, you know, I think, you know, if you like the shortcut for the arithmetic, sometimes people like that one, but like to do the geometric one using the formula. Let's go ahead and do a few more problems here. I know this is a long section, 9.1, but sequences are part of lots of different technical paths. Let's go ahead and do this problem here. Okay, so what is this one right here? Well, it's not arithmetic. It actually is geometric. Okay. where you are dividing by -4. Do you see that? Or you're not dividing by -4, you can say you're multiplying by -1/4. This first number is a1. The formula that we derived is an equals a1r to the n minus 1 power, where n starts at 1. Okay, so this is a sub n equals, a1 is 8, r is -1/4. And then we have to the n minus 1 power. And this is n starting at 1. The formula was pretty simple to do. Your book might do something crazy and write this as something different. You know, your book. So let's say you just did this problem and then your book went like this. This is correct, by the way, but your book went -32, and then you have -1/4 to the n power, and starts at 1. So how they got that is, I mean, how you can verify that this is the same as that one is this is really -1/4 to the n minus 1 times -1/4. Okay, because if you put that together, you get -1/4 to the n. So I'm just saying if your book got a different answer, you can verify it like this, and then you can go -32 times -1/4 is a +8. But for most of you, this is good enough. This generates this sequence. If you put 1 in there, you end up getting 8 times -1/4 to the 0, which is 8. You put 2 in there, you get 8 times -1/4, which is -2. And this generates what you're supposed to do. I will skip the other way on this one because I don't want to confuse people with 2 ways on every single problem. Let's go ahead and do the next problem. Problem number 5. Okay, so look what we have here. We see this, and we're trying to write a formula here. Now, look on the top. What do you notice on the top? Well, you notice 1, 4, 9, 16. If you look at those hard enough, you realize that those are perfect squares. And in fact, you can write n squared. And so, I mean, I'm just trying to prepare you for your homework. This is not arithmetic or geometric on the top. I'm just looking at the top and ignoring the bottom and realizing, hey, wait a minute, there is an n squared there. Okay, so if you see 1, 4, 9, 16, 25, know that that's going to be like an n squared. I better start my n where n should start at 1. Now the bottom, do you see the pattern? It says 2, 3, 4, 5. Well, the gaps seem to be 1. The bottom, the denominators are an arithmetic sequence where the gaps are 1. So I'm just going to go n and then adjust it until it works. So let's see, if n is 1, I want a 2 down there, so I'm going to add a 1 there. Could you get the bottom sequence by doing the formulas? Absolutely. I'm not going to on this problem. I'm going to say there's the answer. The top is neither arithmetic or geometric. The bottom is an arithmetic sequence. But all put together, this is neither arithmetic nor geometric if you're just looking at the fractions. Let's go do another one that has fractions that's a little more difficult. Ooh, look at that one. Okay, so one of these guys doesn't belong. One of these guys looks different. And the one that looks different is one of these ones that have a 9 on the bottom, because something's going against the flow here. I mean, look at the bottom. 3, 9, 9, 81. And then look at the top. 8, 10, 4, 14. So it seems like this guy's the oddball. So what I'm going to do is I'm going to build up that fraction by multiplying top and bottom by 3. So look what I have here. I have 8 thirds, 10 ninths, 12 over 27, and 14 over 81. So they want you to find an explicit formula for the nth term of this sequence. Notice on the top, they have gaps of 2. So the numerators happen to be arithmetic, where D is 2. Now look at the denominators. The denominators, look, 3 times 3 is 9, times 3 is 27, times 3 is 81. That happens to be geometric, where R happens to be 3. So what you can do is you can treat this as 2 different problems. And remember, for arithmetic, you have the formula that says a sub n equals a1 plus n minus 1 times d. And for the geometric one, you have this one that says a sub n equals a1 r to the n minus 1 power. So I'm going to go ahead and do the problem the quick way, and then I'll come back and do it the long way. Okay? So here it goes. The quick way, I see the gaps on the top are 2. So on the top, I'm going to say this is going to be 2n. Now, if I just have a 2n on the top, I'm going to actually undershoot it, because if I put 1 in there, I'm going to have a 2 there, which I'll be 6 below that. If I put a 2 in there, I'm going to have a 4, which is 6 below the 10. So it looks like to get up to where I want to be on the numerators, I'm going to add 6. So if I put a 3 in there, I'm going to get 6 plus 6, which is 12, and put 4 in there, I'm going to get 4 in there is an 8 plus 6, which is 14. Now on the bottom, I have 3, my r is 3, so this is going to be 3 to the n, and let's see if I have to adjust and multiply that by something. If I put 1 in there, I get 3. If I put 2 in there, I get 3 squared, which is 9. 3 in there gives me 27, so this formula right here, and I have to put my starting point, is the formula. Now if you wanted to do this using these formulas, I would go ahead and write these as separate problems and say, oh look, this right here is A1 and D is 2, and I'm going to use this formula which says A sub n equals A1 plus n minus 1 times D. This is 8 plus 2n minus 2, and this gives me 2n plus 6. Bingo, I have that right up there. And for the other one, I would say, we're going to treat this like 3, 9, 27, 81. Here's your A1. I'm running out of space here, so I'll use this formula right here. It says A sub n equals A1, which is 3, times r, which is also 3, to the n minus 1 power. Now look what I have here. I have 3 to the 1 times 3 to the n minus 1. Now it's kind of like when you have an x squared times an x to the 5th, you add the exponents if the bases are the same. So when I add 1 plus n minus 1, I get 3 to the n. Bingo. It's the same thing. So the formulas get you the results that you need. Take a look at a few more problems, and we'll be done with 9.1, which actually had a lot of stuff in it. So look at this one here. This is negative 1, 1, negative 1, 1, negative 1, 1. We're trying to find a formula for this, an explicit formula for this. So how am I going to do this? Well, one thing you can realize is that this thing is geometric, and r is negative 1. Now, if you wanted to do it the quick way, I would just go like this. So here's the quick way. A sub n is negative 1 to the n. And let's see if that gets me what I want. If I put a 1 in there, I end up getting negative 1. If I put a 2 in there, I get a positive 1. So it looks like when I do that, I'm good to go. But if you wanted to use the formula, here's the formula. It says A sub n equals. A1r to the n minus 1, n is greater than or equal to 1. A sub n equals, A1 is this first guy right here, so this is negative 1. And then r is negative 1 to the n minus 1. This gives me negative 1 by what we did in the last problem. You can add the exponent to the n power, which gives me exactly what I had. So that one we found a formula to. Let's go ahead and do our very last problem, and it kind of looks like this problem here. It doesn't, but it does, because it's alternating, you know, between 5, 3, 5, 3. This was negative 1, 1, negative 1, 1, negative 1, 1. And so it's almost like it's this last problem here, but what can we say about this? So that's what we're going to try to figure out here. We're going to try to figure out, let's see, it's not geometric, it's not arithmetic. We can only hope to get this one. We'll see what happens. I'm going to go ahead and start off by taking a guess here that I got negative 1 to the n. Okay, negative 1 to the n is going to give me negative 1, 1, negative 1, 1. And I'm looking for 5, 3, 5, 3. Now, it looks like the difference there is 6, and the difference there is 2, and the difference there is 6, and the difference there is 2. So watch what I'm going to do. I'm going to add 1 there. And what I've done is I configured the light switch differently. So when I put an n equals 1 in here, whoops, let's not put the comma there. So I'm going to start n at 1. So when I put a 1 in there, I actually get negative 1 to the 2 power squared. So when I made that little plus 1, it took everything and switched it around. Now let's take a look at this right here. What is the difference between 1 and 5? It is 4. So I've undershot that one by 4. And I've undershot that one by 4 too, because the difference between that is 4, and the difference between that is 4, and the difference between that is 4. So what I'm going to do is compensate by adding a 4 to that. So we put 1 in there, we end up getting negative 1 squared, which is 1. 1 plus 4 is 5. Then we put 2 in there, we end up getting negative 1 cubed, which is negative 1. So negative 1 plus 4 is 3. And you put 3 in there, you get negative 1 to the 4th, which is 1. 1 plus 4 is 5, etc. And that is the answer. You're not going to get too many like this, but if you get something like this in your homework, start off with the light switch and keep tweaking your light switch until you get your answer. I know there was a lot of stuff in 9.1, but this is stuff that is used in higher math classes. Keep up with your homework. Have a good day.